Let's talk a little bit about steel and this idea of life cycle assessment. This is part of our reading. It's Steel 1, about the ideas of sustainability, maybe a low carbon footprint. And since it's put together by an industry interested in promoting steel, it's a bit jaded by its marketing, but there are some truths in what is presented, and it is a truthful document in its existence. So we just want to touch on this idea of LEED again. Remember, this is a performance standard, but it's not a legal requirement. So a lot of our decisions about selecting materials in our buildings for construction, especially when they're not being LEED certified, are really kind of up to us as the architect, and can make for a really kind of complex set of decision-making requirements placed upon us. So a few things I pulled out of that document that I wanted to kind of highlight. This compared to concrete, structural steel is lighter and stronger material, allowing for dimensionally smaller columns, longer spans, and greater openness. And those are kind of the advantages that we as architects like, the removal of those kind of cumbersome-looking structural materials. But the real one that it punches up here at the end is this idea of a reduced foundation requirement. So if we were to build components out of concrete, they're more massive, and therefore they bear more load on the soil system, and then require increased foundation requirements in order to support the building. So steel can be advantageous to us in reducing that requirement of concrete, another heavy greenhouse gas emitter, reducing the amount of concrete that's needed in our foundation systems. So there could be trade-offs when we're making decisions about whether we're going to structurally create a building in concrete with reinforced concrete, or to do it with structural steel. And once again, that takes a lot of evaluation by a bunch of players in the project. Another always noted by the steel industry, 98% of all structural steel is actively recovered and recycled and reused. And that's probably very truthful. So we can have this idea of reuse up to 93% of domestically produced steel, which is obviously almost this other concept of being domestically, not being imported. Really important consideration in a world of destabilized trading systems and bottlenecks in shipping and that. So steel being made onshore, very important to us, or could be very important to us in being able to meet time and budget on projects. But don't be misled that this is a tremendously green material because it's all recycled. There's still a lot of energy that goes into melting that steel down and refabricating it or reforming it into another structural element, but much lighter than if you were mining ore and the other materials that were needed to fabricate it. And then this last thing, steel framing also offers the most long-term flexibility in that it can be easily strengthened in the field by welding on stiffening elements. And that's really true, and much more true than what you can do with concrete. Very difficult to get the kind of integrity and stiffening within concrete systems. It can be done to some extent with wood systems, but with steel, the ability to weld, to field, attach other structural elements to it, to stiffen it. Say you wanted to remove a beam and make the beam, a column, and make the beam above it carry a greater load. You could easily weld on some flanges to the bottom of that in order to create that kind of stiffness. And sometimes there's enough redundancy in the componentry that distribution of that carrying load to the column that column would still be strong enough. I picked out this image from that PDF just to kind of highlight this idea of one of the issues with steel. It does corrode. So all materials have their issues. Concrete works fine unless there's corrosive freeze-thaw activities that'll expose the rebar and then cause further degradation of it. With steel, unless it's painted or protected, it will oxidize, and this is what it looks like is happening here with this steel. In this case, it's probably not a big deal because this will be enclosed, so the amount of oxide here is very minimal compared to the amount of steel that's there, and once it's enclosed, it will stop rusting because it's no longer exposed to moisture. And it's important, and this is kind of a great image to note how much can be prefabricated and then brought together. This would be very difficult to do in heavy wood kind of truss systems without additional gusseting and elements like that. But once again, not to sell the steel over wood or vice versa. I put this image in because we should have kind of a basic understanding. How do we get to these net shapes of W sections and H sections? So here we're looking on the left-hand side at what's called the roll forming, the hot roll forming of our steel. So we have an I-beam or W-beam being formed here, or an S shape. And each one of those rollers is a progressive series of rollers that manipulates molten metal to the shape that we desire. And so then on the right-hand side here, we can see what it looks like in an actual mill. So going down the center, we have a formed shape coming out of what appears to be coming out of the mill. You can see a host of motors driving these shafts. These shafts may contain additional forming dies. It looks like the forming operation has been completed already. And there's water coming overhead here to possibly, at certain times, to quench the steel or cool it down. And then what you might be wondering is, what are all of these, looks like rolls on both sides? And those are actually the forming dies that create the nut shapes that we would want, whether it be an L shape or a C shape or a W section. These are the progressive dies that would be in the mill outside of the view here, and they're just being stored. They're picked up by crane and placed into the mill in order to do the kind of operations that I'm showing you on the left. Another kind of aspect of fabrication that you should be aware of is we've talked about this idea of built-up sections. So here's a shop probably fabricating something very similar to what we saw in the one of the first slides I showed of the Chinese factory, or excuse me, shipping transfer station, where we had curved roof systems. So here we have, if we look into the into this, basically the center of the image, we have a curved shaped beam which is built up. The flat part is probably cut out with a plasma cutter from solid plates of steel. And then these flanges are bent and welded in order to create these rigid curvilinear kinds of beam systems. They're built on these gray things with the yellow highlighting marking on them. Those are to create a level platform for the fabricator to work on. So this is kind of where the fabrication of our complex steel components would happen, what that factory floor would look like. The next thing I'm going to do is ask you to watch a video here. You can do it now, or you could actually do it at the conclusion of it. And I'll mention it again. I'm going to put this link in on the file. I was going to embed this YouTube video directly in, but then I would just be copying a YouTube video, and that might have copyright issues to it. But this is a relationship between, this is a really well done video by an architect who kind of creates content, and it's about the building of a single family residence in a remote island location, and discussions with the structural engineer. So he really kind of does the back and forth with the structural engineer. I think it gives you a really good feeling about what would be a positive dynamic, a positive level of conversation between the architect and the structural engineer. I think it's really informative. So it's about 20 minutes long or so, and I would ask you to watch that.